Hello and welcome. Today we're going to talk about Laplace transforms of differential equations. So let's start with an example. Our typical differential equation that we're really interested in is this mass spring system with a damper, all attached to an anchor, and I'm going to apply a force to it like that, right? And I want to know what the position is. Okay, so that kind of differential equation is mx double prime plus c x prime plus k x is equal to f of t. All right, so I'm going to apply the Laplace transform to the dE. And recall that the Laplace transform is linear. Okay, and that means that it'll pass through sums and scalar multiplications. So I apply the Laplace transform, mass double prime plus c x single prime plus k x equals f, and it passes right through there, so m Laplace transform of x double prime plus c Laplace transform of x single prime plus Laplace transform, back up there, k Laplace transform of x equals Laplace transform of f. Okay, there's a few questions. X is unknown. And the idea here is I'm going to say that Laplace transform of x is actually equal to capital X of s, right? Our new transformed x function now in rate or frequency space, or as a frequency variable. And the idea here is that x will be easier to solve. Okay, let's see if we can find that. But the problem, of course, is we still have a question. So we don't know what x double prime is, or do we know what x single prime is? So I want to actually, before we can tackle this problem here, I'm going to still need to actually find these two things. So that's actually fairly straightforward to do. What I'm going to do is actually write down the definition for the Laplace transform. So I'm going to start with x single prime. It's going to be the integral from 0 to infinity of x prime of t e to the negative s times t dt. And we can see we can take the antiderivative. We can use integration by parts. So we have x of t e to the negative st. I'm going to apply that 0 to infinity plus s integral 0 to infinity of x e to the negative st dt. We can see that this becomes negative x of 0, and we'll assume that the limit of this as t goes to infinity goes to 0 plus s. And if I look at this object right there, that's actually just the Laplace transform of x. So I can write it like that. So that equals Laplace transform of x prime. And I can box that up. That's my final answer for that. And this is actually very useful for initial value problems because x naught, or x of 0, is known. Okay, so that's nice. All right, it should also be noted, though, that we can apply this formula again, and I won't compute it here, but the x double prime Laplace transform is simply going to be a negative x prime of 0 minus s x of 0 plus s squared Laplace transform of x. All right, and I can box that up as well. Those two facts are very useful, so it's important, I think, to commit to memory. Okay, commit these to memory. Like that. Okay, so let's go back to our problem. Now we have this mass spring system. As follows, and we want to know that state x, right? So what we found is m Laplace transform of x double prime plus c Laplace transform of x single prime plus k Laplace transform of x is equal to Laplace transform of f. All right, well now we can actually sub in our formulas. So m times, let's write it very carefully here. It's going to be s squared capital X minus s x at 0 minus x prime at 0 times, or then plus c, and now we're going to have an s x of s minus x at 0 plus k x. Now we're going to call the Laplace transform of f just our simple capital F of s. So there we go. All right, so that's our basic problem we want to have. And so what we really want to do now is solve for x. That is the goal. And notice the Laplace transform converted a dE to an algebraic equation for capital X. And that's the beauty and the power of the Laplace transform as applied to a differential equation. All right, so I can solve then for x of s pretty straightforwardly. Rather than doing it for a general one, I'd like to do it actually for a very specific one. Let's try it for a specific one. So let's try it for this one. X double prime is equal minus x prime minus 6x is equal to 0. All right, we're going to try a homogeneous equation, and we're going to try it for x of 0 is equal to 2, and x prime of 0 is equal to negative 1. All right, so once we get this all put together, we see that this is going to be s squared x minus 2s plus 1 minus, that's the first term, that's the x double prime term, s times x minus 2, and then we have minus 6 capital X, and that's going to be equal to, and it should be noted that Laplace transform of 0 is 0. Okay, so we can convert everything. Once we get all the like terms, let's get every term involving x. So we have x right there of s, and that's going to be multiplied by, I see there's an s squared, and there's a minus s, and then a minus 6. And then we have to move everything else to the other side. We see we have a 2s, and then we have a plus, or I should say a minus 3 right there. And we can move that over to the other side. I want to notice one thing. That's actually the characteristic equation, right? And remember that s is a rate variable. And of course, that's why it's essentially taking on the values of the characteristic values to a characteristic equation. Now x of s is equal to, well, we can write that down then. It's going to be 2s minus 3 all over s squared minus s minus 6. All right, so that looks like a nice equation. Now let's move to the next page. I'm going to rewrite that. We had x of s is equal to 2s minus 3 all over s minus 3 s. Oh, you know what? Before I'm going to write it down just as before. We have, just as we did in the previous page, minus s minus 6. We can see that this factors, and we can clearly see that it's going to be a 3 and a 2 forming the bottom. So when we factor it like that, we should put a minus 3 and a plus 2 and put s on the other side of the binomial expression. We have a 2s minus 3. Okay, so that looks pretty good. The question then is, all right, so the whole point, right, was the goal is to find x of t, right? We found x of s. The question then is, how do we get back? Okay, so that's pretty straightforward. What we're going to have to do is take an inverse Laplace transform. And that's going to equal x of t. But we're still left with then, how do we compute the inverse Laplace transform of this? Okay, and the answer is pretty straightforward, but we have to use algebra on the expression inside of there to simplify it enough so that the thing is recognizable recognizably something on our transform tables. And I want to now go back and make a comment here. Note, I have a note the following fact. If we look at the table, we find that the Laplace transform of e to the rt is equal to 1 over s minus r. All right? So we get a rational expression like this coming out of it. If I look up there, we see that we do have those same binomial factors sitting up there. So we're going to use partial fractions to break up the expression. All right, so we're going to use one more page here. What we had here is we want x of t is going to equal the inverse Laplace transform of 2s minus 3 all over s minus 3 times s plus 2. Okay. Right, so we're going to have to analyze this rational expression inside that inverse Laplace transform. So 2s minus 3 all over s minus 3 times s plus 2. Now we know that there's an algebraic identity that says that there is a constant a all over s minus 3 plus a constant b all over s plus 2, so that these two expressions are equal to each other. Okay, so what we do is, of course, we multiply everything by s minus 3 and s plus 2, and we get the result here of 2s minus 3 is equal to a times s plus 2 plus b times s minus 3. Right, and this is true for any s value. And so it's true for particular s values. And we can pick. So I would like to pick some s values that make the problem very simple. So I'm going to pick it for s is equal to -2. All right, and then the right-hand side, or the left-hand side, becomes -4 minus 3, otherwise known as -7, is equal to a times 0 plus b times -1. We can see from there that b has to equal b has to equal let's see, did I get this one? Oh, you know what? I made a mistake there. I was confused. Let's back up there. We have a -2 minus 3. So b is going to be equal to 5/7. Very nice. Okay, now I can try s is equal to minus, I'm going to say +3. And that's really nice because it should make this term 0. All right, so we can put that in there. So that's going to be 6 minus 3, that's equal to 3, is equal to, and now we're going to have a times 5 plus b times 0, and that then implies then that a has to equal 3/5. All right, great. So now let's put this all together. My x of t is equal to the inverse Laplace transform of 3/5 all over s minus 3 plus 5/7, that's a 5 up there, not an s, all over s plus 2. Okay, so, sorry, that's the inverse Laplace transform there. So I can use the linearity property. That's 3/5 times the inverse Laplace transform of 1 over s minus 3 plus 5/7 times the inverse Laplace transform of 1 over s plus 2. Right, so note the inverse Laplace transform of 1 over r back up here of s minus r is equal to e to the rt. Okay, so we should be able to use this fact here to guide us towards an answer. And so x of t, and we can see it pretty clearly, is 3/5 e to the what's the value there? That's going to be a 3, so 3t plus 5/7 e to the negative 2t. So that's my solution right there. So we could have gotten that by other methods, but that's the example here that I'll give that shows how to find the solution of a differential equation using Laplace transforms and the inverse Laplace transform. And we see we had to use partial fractions in order to get it. Thank you very much.